Namaskar. Today I will discuss the Euclidean domain and unique factorization domain. What is the definition of Euclidean domain? An integral domain is a commutative ring R with a unity containing no divisor of 0. Containing no divisor of 0. If A multiply B is equal to 0, for AB belongs to R, then either A is equal to 0 or B is equal to 0. Next one, definitions. Let R be a commutative ring. AB belongs to R, A is not equal to 0. We say A divides B if there exists C belongs to R such that B is equal to AC. We write A divided by B, in this case is called the factor of B. A divided B, in this case called A is factor of B. Next definitions. Let R be a commutative ring. AB belongs to R and 11D belongs to R is called the greatest common divisor of A and B. If D divides A and D divides B. Second, if there exists C belongs to R such that C divide A and C divide B implies that C divide D. We denote this by D is equal to the GCD of AB. Next remark, GCD of AB need not be unique in R. For this, consider R is equal to Z theta Z 2 multiplication modulo 8 3 is equal to 6. 2 divide 6. 2 multiplication modulo 8 is equal to 4. 2 divides 4. Again, if C divides 6 and C divide 4, then C divide 6 minus 4. Thus, 2 is equal to GCD of 6, 4. Again, 1 multiplication modulo 6 is equal to 6 and 6 multiplication modulo 6 over 8 is equal to 4. Hence, 6 by 6 and 6 by 4. If C by 6 and C by 4, we get C by 6. Therefore, GCD of 6, 4 is equal to 6. Hence, 2 and 6 are GCD in Z6 for the same pair 2, 6. Next, existence of GCD for any pair AB in a commutative ring R is not compulsory. Consider the ring R of even integer. 4, 6 belongs to R 2, 4 T by 4 in R, but 2 does not divide 6, as 2 multiply 3 is equal to 6, but 3 does not belongs to 6. Then GCD of 4, 6 does not exist in R. Let R be a commutative ring with unity. AB belongs to R are called associate if A is equal to कोई scalar multiple of b, that is a is equal to mu b for some unit u in R. U is a unit in R means multiplicative universe u inverse of u exists in R. Next one theorem. Let R be an integral domain with unity. If d1 is equal to GCD of AB in R, then d2 is equal to GCD of AB in R1, d1 and d2 are associate. Only part. Let d1 is equal to GCD of AB and d2 is equal to GCD of AB. Then d1 divide A and d1 divide B, d2 divide A, d2 divide B. Therefore d1 divide d2 and d2 divide d1, and d1 and d3 are associate. Let d1 and d2 be associative and d1 is equal to GCD of AB. d1 is equal to mu d2 for some unit u in R. Hence d2 divided by d1, we get d2 divided by 42 and d2 divided by 32. Next definition. Let D be unique factorization domain. A non-constant polynomial f of x is equal to e naught plus a1x plus dot dot plus anx raised to n in D of x is primitive if and only if common divisor of all the ai's in example 4x cube 4x square plus 7x plus 3 is a primitive in Z of x. 3x square plus 6x plus 9 theorem. Let D be a unique factorization domain. Let f of x belongs to D of x be a non-constant polynomial. Then f of x equal to c into g of x, where g of x is a primitive in D of x. The element c is unique up to a unit factor in D, and the polynomial g of x is unique up to a unit factor in D. Let f of x equal to a naught plus a1x plus dot dot plus anx raised to n. An is not equal to 0 be a non-constant polynomial in D of x. The coefficient a naught a1 dot 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 an in D can be factored into a finite products of irreducible in D uniquely up to order and associate. Assume that each coefficient of f of x is factored in this way. Let p1 of x denotes the irreducible in D appearing for the factorizations of one coefficient. If p1 provides all coefficient, then p1 will be the factorizations of all the coefficient Assume that on other associate p1 is equal to Gauss theorem. Let D be unique factorization domain. F of x, g of x belongs to d of x be positive primitive polynomial. Then prove that f of x into g of x is also primitive polynomial in d of x. Let f of x equal to a naught plus a1x plus dot 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 g of x equal to b naught plus b1x plus dot 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 b two primitive polynomial in d of x. Let h of x is equal to f of x into g of x. Then h of x equal to a naught b naught plus a1 b naught plus b naught a naught b1 plus dot 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 and so on. And therefore, thus we have proved that any reducible polynomial p belongs to D will not divide all the coefficients of h of x is equal to f of x into g of x. Hence, h of x equal to f of x into g of x is a primitive polynomial in d of x, and this is proof. Gauss theorem. This is Gauss theorem. झोप पे चले रात्र भर झोप नहीं, पाऊस नहीं.